Okay, last week of class. First announcement is I just why is it doing that? I just changed the due date for homework 15 so that it so that it's due on Wednesday night. Homework 15, which is moments of inertia, will be covered on the final exam. So you want to finish that so we can talk about it on Thursday on our last chance day of review. What I'm thinking about the final is it's a little, I'm not sure I'm going to be able to get it together, but I have all the questions and what I'm thinking about the final is that you may have a choice. Like you could do a traditional final. I don't know. I'm still thinking it through. I don't know what makes sense. I don't know how much, what would you guys rather have, a multiple choice final or a traditional final? It's on Wednesday. Yeah, it's at 1 or something. I don't know. 1 o'clock. 1 to 3. Why do you have to work then? What? Huh? Oh, 10:30 to 12:30. Yeah. Well, I can. You can take the final another day if you want. I will probably have some alternative times for the online students. Well, so I want everyone to take the final, but if you've got a 93 or higher, then the grade isn't going to count for your final. But I would like you to take it and do the best you can so that I can kind of just, well, maybe what I should do is make the people that got 93 or higher do the multiple choice final. Because I want to get a control. I want to just sort of see how that is. It won't, like, you're still going to get an A, but I want you to do the best you can. I want to see how well you can do on that. And then I probably will throw some multiple choice questions on the final, but not give you the same multiple choice final that I'm eventually thinking of. I don't know, I'm still thinking it out, but maybe like 10 or 20 multiple choice questions and then a bunch of, what I actually was thinking is ideally, because, you know, having a bunch of multiple choice questions to cover all the stuff we've done already, and then just have computational problems for moments of inertia and centroid and stuff. But maybe I'll throw 1 or 2 representative ones in there from earlier stuff too. I don't know. I don't know what makes sense, but I kind of like the multiple choice stuff just because it covers a lot more, you know, conceptual ground than, like, typically what I've done is like maybe have like 6 computational problems, 6 or 7 computational problems, and a bunch of multiple choice. But having fewer computational problems and more multiple choice would give us more coverage, I think. Anyway, but let's talk about tests tomorrow. That's the important thing. So tomorrow's test has 3 computational questions, and it has 5 multiple choice questions from chapter 7 and 8. You got one. Weren't you here on last week? Practice test 4, you got a practice test 4 last week. So that's what we're going to go over today. If you have any questions on practice test 4, if you need a copy, I still have some here. And any other questions that you might have, if anyone did any moments of inertia stuff, I'll take that. I think the quiz is, there's a quiz. I think some people didn't do the quiz. Did some people not do the quiz? Y'all did the quiz, right? Quiz last night. You did it last night? Okay. Does anyone want to go over the quiz? Anything? We can go over the quiz. We can go over any of these practice problems you might like. The solutions, I can just show you the solutions if you just want to look at the solutions, or you can pull them up on your own computer and then ask me if something doesn't make sense. What would be helpful for you guys? Yeah, Nick. That's true. Yes. Yeah, centroids are on the exam. Where does it say 7 and 8? I did say that earlier. But if you look at this thing, it says covered assignments 11, 12, 13. So you should check out the solutions to those assignments. And 13 is the centroid assignment. Yeah. And the practice test has centroid problems on it. Sure. Would you just like to look at the solutions, or you might have developed them? Here are the solutions. Number 3. Determine the smallest force P needed to either move the box up the ramp or make the box tip clockwise. So it's the smallest sort of force for impending motion. Is this sufficient, or would you like me to go through and develop it? Uh-huh. Yes. And I think like the whole moment part doesn't that mean that like the center of gravity is different? Or it's like its moment would be different somehow? I don't know, I think the angle is confusing me on that. Well. Yeah. When you tilt the axis, that's the question. What happens to the components of the x and y of the weight, right? I mean, you have a vector here, right? And it's of a certain size. In this case, it's 2940. But then when you tilt the axis, you're going to have, you know, this thing is going to have, you can think of it, if your axis is going like this and like that, then you're going to have a component of that that's, you know, that's your W sub y, and a component that's this way, which is your W sub x. So it's just being comfortable with that operation, right? So that when you do the moments, they're pretty straightforward, right? I don't know, if you want, I could develop any of these things from scratch. You've had them, you've looked at them, you've presumably looked at the solutions. This is a chance to kind of clarify. I don't want to just bore you by solving things that you already know how to solve. I want to help this clarify things for you. Yeah, Isaac. For you, it's going to be, for you, I predict it's going to be easier because you're more worried about your grade. So, but now you're really worried about your grade. And so you're going to study extra hard. So it'll be easier. That's what I predict. Yeah. I predict you're going to get a nice sandwich in the morning, and Ali will have good soup for dinner. Yep, go ahead. Yeah, there's some complicated operations there about sliding and tipping, right? Because there's assumptions, right? There's things that are happening when it's sliding or tipping, right? And when it's sliding, what are the assumptions about that? This is an example of sliding here on the left. When it's sliding, what do we assume? Yeah, this distance x here is less than half of the width of the box, right? X is the distance that the normal force is drifting over to keep the moments okay, and therefore the sum of the moments 0 is still true, which means some of the moments about this point. What do we do at about 0.0? We could do the sum of moments about 0.0, which means that you've got n times x going counterclockwise, and you have p times h going clockwise, and you also have 3/5 of w times the center of gravity, the center point here, which is 40 centimeters, right? So plus 3/5 w times 40. Yep. X less than 20 centimeters means that the sum of the moments can equal 0, because if it's tipping, well, you can still find that point, but when it's tipping, X is at or is equal to or greater than 20 centimeters. And if it's greater than 20 centimeters, then that means the sum of the moments can't be 0, right? That's why it tips. Right, if the normal force has to move off of the box in order to keep the box from tipping, the box is going to tip, is basically what that's saying. Isaac? Yeah. Yeah, the normal force is normal to the surface of contact. Yeah, and the weight is pointing down, but not opposite. In this case, because it's tilted, the weight is pointing down, and the normal force is pointing tilted. So there's a component of the weight that's pointing opposing the normal force, and a component that's going parallel to the contact surface, right? Yes, that is correct. Yeah, these are really kind of deep questions when you get down to them. Yeah. To the weight, right? It would only be if the box was on a flat surface, a horizontal surface, then there would be no horizontal component to the weight, right? There would be no x, there would be no wx. Yeah, so I don't know, did you guys get a chance to look at them? Would you like to just work in small groups on them, on these problems, and call me over if there's any questions? Or I don't know what's better, or you want me to just solve some of them, or what? The centroid problem on the sample test? Oh, these are the answers. Let's pull this up here. There's two. Centroid of the shaded area shown. Okay. Centroid, right? So the equation is 9 minus x squared of this line. So we have to decide, do you want to do a horizontal strip or a vertical strip? Well, you're free to explore and figure out which one makes sense, right? Yeah. When you get to moments of inertia, you don't always have that freedom, because for some of the formulas to work, the rectangle has to have a base on the axis, that kind of thing. But in this case, I don't see why you can't do it. It's just one of them may have a harder integral than the other. Right, so y equals 9 minus x squared. It seems to me a vertical strip is going to be easier, because if you do a horizontal strip, you got to solve for x, which is going to have a square root in it. Right? Unless you like integrating square roots, you can do that, but it's not the funnest thing if you don't have to, right? So this vertical strip is going to have a height of y equals 9 minus x squared. This is our dA. This is the x tilde. This is the y tilde, which is going to be what? Y. What is that? What is y tilde, everybody? What does y tilde represent? 70. What does y tilde represent on these? Jose, what does y tilde represent? Center of what? Center of what? Yeah, it's the centroid, the vertical part of the centroid of the differential area that we're looking at, of the dA. The y tilde is the centroid of the little dA rectangle in y, right? Which is what? Y over 2, which is 9 minus x squared over 2, right? And the x tilde is what? It's just x. In other words, I give you an x, and you can tell me, if I ask you, there's a little vertical strip there at x equals 0.5 or 1.5, right? If I'm talking about x equals 1.5, you can tell me what's the height of that rectangular strip. It's just 9 minus 1.5 squared. You can tell me where the centroid of that rectangular strip is. It's going to be right at the x, because it's so narrow, it's right at whatever x you're looking at, right? So in other words, x is sort of given. I don't know if this makes sense. I think everybody sort of gets this. What this sort of means is, given some x, the x tilde is going to be at the x, the y tilde is going to be at 9 minus x squared over 2. And the dA is going to equal 9 minus x squared times dx, right? All this is sort of assuming that we're giving some x. In other words, if x equals 0.1, you can find, oh, that means that rectangle has an x center of mass of x of 1.1, and the y tilde is at this point, and the dA is going to be like that. You can do that for all these infinitesimally small rectangles that you're doing, and that's what calculus is doing for us, Isaac. Why isn't x tilde x over 2? I think you're not getting what I'm saying. if I told you, Isaac, that there happens to be a little, let me just draw this again here. Here's a curve, and I told you, Isaac, I know that there's a little vertical strip right here located at x equals 0.1. And I asked you, Isaac, where is the centroid of that little rectangle, infinitesimally small rectangle, located in x and y? What's the x tilde of that? Would you say it's at 0.05, which is right over here? Or would you say it's at 0.1? Your question is, will it always be given in the format that you always have the position of that? I'm not sure what that means. X is already in the middle. Yes. If it's given, well, you would have to give me an example. One thing I think you might think of is, what if it's a horizontal rectangle? Then the y tilde is just y, but the x tilde is going to be halfway, that midpoint of that strip, right? Yeah. If it's a vertical strip, the x tilde is just x. If it's a horizontal strip, the y tilde is y. Yeah. Mm-hmm. Cool. So really, this is the y tilde, x tilde, and the dAs, and you got to figure out all those things so that then you can find the area is just the integral of all the dAs. The x tilde is the integral of the x bar. Actually, we should say x bar a, which we can't, these are the moments, right? This is going to be the integral of the x tildes times the dAs. And the y bar a is the integral of the y tildes, which are 9 minus x squared. This is a little more challenging. Right? But not too hard. You got to square that polynomial and all that stuff. Mm-hmm. Yeah. No. Is this hard? That's not that hard. Yeah. Well, some of the homeworks had like those line integrals could be challenging. Yeah. No, there won't be a one like that. And if there is, you just got to set up the integral. If you can just set it up, that's really good. If you can't do the integral, that's a small number of points. But being able to, I think the important part here is conceptualizing, because you can use Wolfram Alpha to do an integral for you. The engineers will do that. They're not going to, if it's a hard integral, they'll find some tools to do it for them. Seven? Would the limits on y bar be 0 to 9? What do you guys think? Good question. Should they be 0 to 9? Why? Because you're using a dx. You're using a vertical strip, and a dx is going to have to go from 0 to 3. The dx's don't go from 0 to 9, they only go from 0 to 3. David? Yeah, we can do this whole thing again with horizontal. Why don't you all try to do a horizontal strip and just set up the integral for that? It's going to take a couple minutes. What do you mean, things you got to know? These two equations, you mean? You have to know how to do that. Is that what you're saying? Before putting in the equations, what do those integrals look like? I don't know what that means. Try to rephrase that for me. No, please. So, yeah. Well, we're just doing the, I mean, this is the equation for x bar a. So we would evaluate that integral and come up with a number. Is that what your question is? I'm not sure what that question is. So in other words, you could evaluate this integral, it's going to equal some number, right? And then x bar is just going to be x bar a over a. And then y bar is going to be y bar a over a. So that will give you another number. And those are the numbers that we're trying to find for that problem. I'm not sure if that's going where you're asking or not. Ollie? Yeah, sure. Yeah, so the other centroid problem is this. So if I give you this, you know, oh God, it looks hard. But it's not, right? You can have the formulas for a semicircle on your sheet. Yeah, you got a cheat sheet. And I think you're worried that you might not have the right shape on the cheat sheet and all that stuff. But if there's a problem like that, I'll just put it on the board. I'll give it to you on the homework, on the test, so that you don't have to worry about that. But you should understand what that means. You know, we did this a couple of weeks ago, right? Did we do this before Thanksgiving or after? Yeah. So it's just a little practice. So so the centroid of a semicircle would either be given to you, and I guess I probably on the practice test I should add that so that. I saw a hand go up there. Was that something I should address now or later? So here's the centroid of a circle. It's 4r over 3 pi of a semicircle. I will save this in case anyone wants to ask about that later. And then we'll make a new one here. What I like about these problems is they really illustrate how these things actually work. So what do I say, 4r over 3 pi, right? So there's only 2 shapes. And we can make, the best thing to do is make a table, right? So the table is going to be shape and we're going to have, what is the x tilde? It's the same thing, right? The x tilde and the y tilde are the centroid of each shape, just like the x tilde and the y tilde are the centroid of the differential rectangle when we do the calculus problem, right? And actually, I think what we do is we call it Yeah, we'll just call it x tilde, and then we'll have the area. And then we're going to also have to compute the x tilde a, the product of the area and that, which is basically a moment calculation. Right, and that becomes our table. So we can call this shape 1 and this shape 2. What is the centroid of shape 1, that triangle, relative to the origin? What's the x and y of the centroid of that triangle? It's 9 inches tall, 3 inches wide. Where's the centroid of that triangle? Why don't you all write it down? Pop quiz. It's just by inspection, you can kind of just come up with it, but I want everyone to try it, and you can tell if you got it right or not. What's the centroid of that triangle? David? 2,6. So the x is 2 and the y is 6. Does everybody agree? What do you think, Ali? What'd you put? Still thinking, Isaac? 2, 3. So let me just illustrate where you guys are putting this centroid. Okay, so David says, so here's 3, and here's divide this in thirds, right? This is 6, this is 3, this is 3, and this is 1, and this is 2. So David says that the centroid is like right over here. Thank you. Instructor is wrong here. You're right. I said it was width of 3, but it's the width of 6, isn't it? So this is 2, 4, and 6. So David says it's right here. What do y'all think? And everyone agrees it's not 2, 3, because that would put us right here. Yes, thank you. Yeah, it's a triangle, and you go a third of the way from the large side across to find the centroid in either axis, right? So that's not too bad. Pardon me? Yeah, for a triangle which has a fat side and a point side, right? It's 1/3 of the way across from the fat side to the point side, starting from the fat side. Well, this is 6. So this is 6. That was my mistake. I just said, no, it's 3 inches across. Oh, but it's not. It's 6 inches across because it's a circle with a radius of 3 right there. As David perceptively noticed. So a third of 6 is 2, right? And this is 9 inches from this fat horizontal part to this point. And we got to go a third of that 9 inches from the fat side, which is going to be 6. Or 3 from the fat side, which is going to be 9 minus 3 gets you to 6. Okay. Now you've located it. And what's the area? $27, right? Okay. Let's try the semicircle. Shape 2. What's the x tilde of the semicircle? Jose. That was not a confident 3. Is it 3 and something else or just 3? Okay. Everyone agree? Okay, Savneet, you get the challenging one. What's the y tilde of that semicircle? Well, it does say 4r over 3 pi here. That's the center, the centroid of that semicircle, yeah. If the semicircle is centered at the origin, then the height is 4r over 3 pi, right? So Savneet, you're gonna fill us in here. What's the answer? You like 4 pi? Okay. So you want me to put 4 pi right here? Four over pi. That looks better. 4 over pi. Okay, and well, let's just think about it. 4 is approximately, well, pi is approximately 3. So say 4/3 is going to put us at like 1.33, right? So Savneet, you're saying, because this is 3, here's 2, here's 1. You're saying the centroid of the semicircle right there is like right about here. Does that look right to you? Okay, where should it be? Between 3 and 6 on the y-axis? This is the semicircle, right? We're just looking at this semicircle right here, right? We want to know the centroid of this thing, which to me, it looks like it's right about here. What's that point? More than 9, right? How much more than 9? Well, how about this much more than 9, right? So like 9 plus that, because you got to offset this thing by 9 because it's 9 units away from the horizontal axis. Yes. 4 over pi plus 9, whatever that is. Why do we say 4 over pi? Because r is 3. Yeah, that's a formula that you get from a table, like one of these. Where was I? Here I am. Okay, and what's the area? Well, the area is 1/2 times pi r squared, so it's 1/2 times pi times 9, right? 4.5 pi, whatever that is. This stuff you can do on your own. That's just multiplying x tilde times the a, right? And then you got to do the sum of all these things, right? So then the sum here is important. This is going to give you the total area of the combined shape. This is going to give you the total moment x bar a. It's going to be total moment y bar a, which you can then use to find the x bar and the y bar of the whole figure. And you should apply some common sense reasoning so that if you get a number that says it's at like 4, 1, you know, which is like right over here, that you made a mistake somewhere. because the centroid of that thing should probably be in the middle of it somewhere. What is a centroid, Ali? The geometric center of the body, right, where it would sort of balance if you could hang it from there. You know, is it always on the body? Yeah. So suppose you had a very sinuous, snaky shape, or I don't know. It's a piece of metal that you might cut out for a sculpture. I don't know. It's a winding river, or it's a worm. What's the centroid of a worm? What's the centroid of that? Should be on the body? Not necessarily. Can't say for sure. Where's the centroid of that? Here? Does it have to be on the body? Why? Well, but some bodies can't be balanced from the body, you know, you can't. Yeah, sometimes the centroid could be off in space. Could be over here. How's that possible in real life? Well, it's not like a physical, I mean, it's a point, you know, like it's not physics, it's just math. I mean, as far as the physics go, if you think of this as like a boomerang, I think if you throw this thing, this centroid is sort of what it would be revolving around. If you threw it as a boomerang, I think it would be revolving around, you know, the geometric center of itself. You know, if you throw this thing, and that centroid would sort of track that, even though the shape is doing some complicated stuff, the centroid would be sort of moving in a very smooth projectile kind of motion, even though the thing is sort of flying around its centroid. Does that make sense? We're not so much concerned about balance. What the centroid is, I did use the word balance as a way of expressing kind of what it means geometrically. It's sort of a balancing point of the object. But some objects are confined that they can't, you know, if you talk about a wire, the balance point, what I meant with, like, for a triangle, you know, if you find that centroid for the triangle, you could hang it and it would hang flat. It would, you know, hang perfectly horizontal because there's equal mass on the other side. All the moments are sort of balancing out, right? But for a wire, some wires, there's no way you could hold that wire so that it would be flat, so that it wouldn't drop, you know, right? There's no place you could do it. I mean, you could if you could hold it like right here, but you can't hold it there. But that would be the point which is defining its centroid. That's the point. When you do it, it's going to be off the body, but it finds its balance point off the body somewhere, which it's just sort of what it is. Yeah, Isaac. We're defining centroid as a balance point. We're defining centroid as I mean, what the centroid really means is I mean, it comes down to the equivalent systems kind of view that we used earlier in the semester, right? when we try to find a way of reducing a force, and I think what was really helpful is when you saw those that one problem in the homework. Remember this one where it had the plate that was suspended by a cable and held up by a roller. Remember that one? And in order to find, they told you like what the mass of the plate, but you had to figure out where it was, where the center of mass was located, so that you could find the load on the supports and stuff, right? You remember that problem, right? On the homework? I could show it to you again if you want. Well, we're not trying to balance that thing. What we're trying to find is the point where we'd put the equivalent force of its weight in the system, so that we would be able to figure out what the support reactions are. Now it happens that that point is sort of geometrically is kind of like the point that it would sort of balance horizontally if you did it, but we're not trying to balance this thing. Unless you're trying to make some sculpture that's going to balance in some weird way, you could use these things for that. But that's not our goal. Our goal is to find, the load, the support reactions for the structures that we want to build. And for those, the centroid is helping us find the concentrated point where all that thing could be effectively applied, so that we can simplify our calculations. I think Jose and then Isaac.
It'll be kind of hard, picturing where center is, kind of do it. But can you picture how, like, let's say if you were to give us a question where you say, what is this actually? How would you figure it
out? Well, you already did a bunch of multiple choice questions involving centroids last night, right? Well, those are the same kind of questions you'll find on the test. Yeah. Anyone want to go over the quiz from last night? Yeah. Okay. So let's try that out. So Isaac is asking a question which is interesting. Oops, it is here, and let me just grab some empty. Space here. Which is, his question was, if you have these two shapes here, would they have the same centroid? Same height and width? You can't draw it that way, but I can try. So if this is 3, and this is 3, 3, 3, will they have the same centroid? What do you guys think? David says no. Ollie says no. Jose, what do you say? I don't think so. I don't know. Well, we know you could find out in like 5 minutes using what we already know, right? You could find the centroid of this thing if you put some numbers on it. What is this, like a half? 0.5 thick or something? It's sort of thin, right? And we know that the centroid of the rectangle, the triangle is going to be here, like right at this point, right? At 2, 1, if this is the origin, right? And we know the centroid of this rectangle is going to be like here. Centroid of this rectangle is going to be like there. And you could do that table thing to find out what it turns out to be. But you got to put some numbers on the thickness and all that stuff. Oh, what if the thickness was negligible? All right, well, that's a good thing. In the limit, as the thickness approaches 0, then you're back to a wire. No, it wouldn't be completely different. Actually, that's a good question because we can find that a lot easier. All right, because we can identify exactly where these centroids are, right? Where's the centroid for this part of the wire? What's this point here? 1.5 comma 0. And this point here, what's that? Nope. 3 comma 1.5. Right? Now, you got to give these things an area, or you can call them a length, right? We'll use L now for the thing, right? So we have our shape. We can make that same table, right? We have our shapes. 1, 2. We'll give them a length. We'll give it an x tilde and a y tilde, and then x tilde L and y tilde L, right? These are the tools that you have now. You can find these things out. They're not that hard, right? So the L here is going to be 3 for each one. Each one has a length of 3, right? And the L corresponds to kind of like the mass or the the total weight of the thing. Yep. X tilde for shape 1, we'll call this 1 and this 2, is 1.5 and 0, and this is 3 and 1.5. Now you got to multiply 1.5 times 3 is 4.5, and this is 0, right? 0 times 3. And then x bar L for the second figure is 9, and for the y bar L, it's 1.5 times 3 is another 4.5, right? So now we have to take the sum of these things. The total sum is 6. And the total y bar L is 13.5, and this is 4.5, right? So this is allows us to find x bar is going to just be 13.5 over 6, right? And y bar is going to be 4.56, right? 6 is the total length.
And that will give you the point of the center.
Yeah, and that works out to be about, what is this, 2.3 or something, right? And this is going to be working out to about 0.75. Oops. Does that seem right? So it's located like, should be somewhat symmetrical. Maybe this is 2.25, huh? This is probably 2.25, isn't it? Yeah, that would make sense. So it's located, here's 1, 2, it's located like right about here. So it's actually, it's lower, I think, isn't it? This is located at 2 comma 1 compared to 2.25 and 0.75. It's a little bit. So this one is appearing, the triangle is sort of appearing here, and the wire is appearing there. Not the same. Because it's a different distribution of material.
So I can't tell through your drawing, but the point that you do, like in the middle of the wire, the wires.
Yeah.
Like if you put a line from the one that's on the x-axis and the one that's on the vertical line, you do a line in between them, and you found like a vector between those, like a base vector on the bottom of the because you get the point in the middle.
Maybe you should draw what you're saying. I'm not sure what you're saying.
Like,
let me change the color here.
Like, so that's 1.50, right? That's
1.5.
1.5. So if you did like,
if you drew a line between those?
Yeah. Like if you
so if you drew a line here,
yeah,
is it going to be on that line?
No.
Doesn't look like it.
Even though we did.
Yeah, doesn't look like it.
I didn't think it would be.
Yeah.
But it actually makes more sense that it's not.
Yeah, it doesn't have to be.
Because it's not about the center of that line.
Yeah.
So in short, it's not the same.
In short, it's not the same.
Okay.
I think we've established that. Cool. Okay. You have negative area, then the area is negative. And then the product of x bar times or x tilde times the area is also negative.
Which one? The area.
Well, if you have a hole, I mean, you're, because that's the thing, if you have a negative, if you're modeling something like that has a hole in it, it makes perfect sense because suppose you have something like this, right, with a hole in it. If you call this, you want to turn something in? Yeah. Awesome, thank you. Cool. If you're doing this thing, whoops, if you're doing this thing, right, and this is shape 1 and this is shape 2, and it's a hole, your table is going to have an area, you know, and well, if this is like 5 by 5 and you're gonna call this area 25, that's not correct, is it? The whole body doesn't have an area of 25, right? Because you got a hole there. And if this thing has you know, a radius of 1, this thing is going to have an area of minus pi. Because when you want to find the total area, you got to think, well, of course, the total area is going to be 25 minus pi. Yeah. So the x bar, you know, so if the, you know, in order to do this thing, you're also accounting for an inappropriate material when you're doing this moment calculation, when you ignore the hole for shape 1, right? So you have to remove something also when you do shape 2. So whatever this is going to be a negative number as well, because the area is negative. Unless, of course, it's on the left side of the x-axis. If x tilde is negative, then you'll have a positive there, but it'll all work out. The math will be, in that case, the math will actually take care of it. Yeah.
Something real quick.
No.
No, so I'm 14 now.
14.
But
I'm like, how do you come up, like, how do you print it in this one? Because he doesn't have it, like, printed out.
oh, how did you print it? You can just print it right here.
That's kind of from the color, or is it?
No, like,
You can just print it. You can log in and print it right here.
yeah, or something like, you know how you print it out from this? Like, you probably things.
Uh-huh.
But how do you do that? So
Well, it's on
the
the,
file is not different.
no?
No, it's on the
Oh,
Then I'll click on.
did you find it somewhere? I don't know. Maybe he found it somewhere. I don't know, but you can just sketch it or whatever. It's not in there?
You know, because I was looking for file on 13.
I mean, homework 14 or homework 13?
I couldn't find 13.
Oh, did you go look here? This is where everything is.
Yeah.
Here's a 14.
And where is that? Hmm. Yeah. So,
Is that not in the,
so how did you find it?
well, I don't know. This is,
This is the
well, there is a lecture here.
yeah.
And here's a link to assignment 14, which takes you right there.
Okay. Is it like same thing for like school?
This is the view. I mean, this view you'll also see. You should. It's published.
Okay.
All of my things are linked there. The homework actually doesn't have the link. Should
Yeah,
probably change that.
Yeah, homework is
Right, but the lecture does. All the homeworks are linked to the lecture.
So like, you have negative here, oh, here, negative something. But if there's a hole,
Mm-hmm.
that's something that it's not part of it. You know, like, if you go the area, so, like, there's no hole, you have a circle there.
Mm-hmm.
It's not a hole, it's a spot, it's solid.
Mm-hmm.
But there is not like, or it has to be like, in order to back it.
Draw me the exact shape that you want to, that you have a question.
Like, circle, you have a rectangle.
Mhm.
If you have a hole here, what I'm saying is, it's not a hole, it's just a circle here. But no, not saying
So someone drew a circle on it,
no, yeah.
but it's not a hole. Well, then it's just a rectangle with a circle on it. It's your rectangle.
So do you
Just forget about it. If it's just a drawing, it doesn't affect the mass of this thing.
That's just
It's just a question. You said it, not me. Okay, I think we're done.
So tomorrow we have 4
Yes.
and also multiple.
Yeah.
How many? Like last
I think there's just 5. I don't know. Yeah, probably just 5.
calculation problem or it's like 4?
3 calculation problems.
3?
Yeah.
Okay.
Yeah. Mm-hmm.